All right, class, without further ado, the Chapter 3 videos. So in Precalculus, we're only going to cover sections 3.1 and 3.4 from Chapter 3. Those focus on polynomial and rational functions. We have seen polynomial and rational functions before. Now we're going to go into a little bit of a deeper dive into how they are graphed and determining information given our functions. Section 3.1 is about polynomial functions and models. So a polynomial function of degree n is defined by f of x equals a sub n, where a sub n is our leading coefficient, and x to the n, that's our highest degree, and it goes on and on, where a sub 0 is our constant term, so it doesn't have a variable. All of those coefficients, those a sub n minus 1, 1, 3, those are real numbers. Our leading term cannot be 0, and n is a whole number. So for our function to be a polynomial, n has to be a whole number. Remember, our whole numbers are 0, 1, 2, so on and so forth. The graph of every polynomial is continuous. For us, that means I can draw it without picking up my pencil. Its domain is all real numbers. What we need to be cautious of is its range. We've seen polynomials before, linear functions of the form f of x equals mx plus b, and quadratic functions of the form f of x equals ax squared plus bx plus c are polynomials. So the coefficients, that's a typo, are our a sub n's, a sub i's. Our leading term is a sub n x to the n, where a sub n is called the leading coefficient. I think I mentioned that before. Our a sub 0, that's our constant term, and the degree of our polynomial is n. That's going to be the largest power on our variable x. So let's determine which of the following are polynomial functions. If they are not a polynomial function, I want you to tell me why. And then we should write each polynomial in standard form, meaning that it is largest to smallest degree. And then I want us to identify our leading term, constant term, and the degree of the polynomial. So lots of steps. So let's look at A. Is A a polynomial? Yes, it's a cubic. It's a degree 3 polynomial. It's already written in standard form because it goes from smallest degree of x to largest degree to smallest degree. My leading term is going to be 5x cubed. My constant is -9. And my degree is 3. Next, let's take a look at example B. f of x equals x plus 2 minus 3x to the 4th. Is this a polynomial? Yes, but it's not written in standard form. I want my largest degree term first, and we go from a decreasing degree. My leading term in this case is -3x to the 4th. My constant is 2, and my degree is 4. Next, let's take a look at C. And we're going to switch colors. G of x equals the square root of x. Well, remember the square root is x to the 1/2. And part of being a polynomial means I have to have a whole number power. So this is not a polynomial. D, I have h of x equals x squared minus 2 over x cubed minus 1. This is a rational function, but is it a polynomial? No. Remember, I need my domain to be all real numbers. And that would not be the case. Here I would have to exclude 1 from our domain. Let's take a look at E. G of x equals 8. Is this a polynomial? Yes, this is a horizontal line, It just so happens that the leading term and the constant term are the same thing. They're both 8, and my degree is 0, but this is still a polynomial. Next, I have h of x equals negative 2x cubed times x minus 1 squared. This is going to be a polynomial, and let me show you why. So I have negative 2x cubed, x squared minus 2x plus 1. I have negative 2x to the 5th plus 4x to the 4th minus 2x cubed. So this is a polynomial. My leading term is negative 2x to the 5th. My constant, it doesn't have one, would be 0. It's not that it doesn't have one, it has a constant of, oops. It's not that it doesn't have one, it has a constant of 0, so keep that in mind. And my degree is 5. A power function is a monomial function, mono meaning it has one term, of the form f of x equals ax to the n, where a is a real number, a doesn't equal 0, and our degree greater than 0 is an integer. So linear horizontal equations, functions, so for example, like f of x equals some constant, are not a power function because their degree is 0. But here are some examples of power functions. So here are some properties of power functions. If my degree is even, my function is symmetric to the y-axis, my domain is all real numbers, and my range goes from 0 to infinity. My graph will always contain the points negative 1, 1, when x is 0, y is 0, and when x is 1, y is 1. Think about this as kind of as our most basic quadratic. An odd function is symmetric to the origin. Its domain is negative infinity to positive infinity, and its range is also all real numbers. The graph will always contain the points negative 1, 0, 0, and 1, 1. For this, we have two examples. We have f of x equals x, because that's to the degree of 1, and f of x equals x cubed. If you look at the graphs of both of these, this one's just a line, right? But they will all contain these 3 points. Same holds true when we increase our powers. If I was to say have x to the 4th and x to the 5th, notice how x to the 4th kind of looks like x squared, but it's got a flatter bottom, and x to the 5th is just stretched a little bit skinnier. Let's talk about zeros of a function. These are the x-intercepts of our function, so where our graph crosses the x-axis. If f is a function and r is a real number, for which f of x equals 0, then r is called a real 0 of f. This will make x minus r a factor of f. Note, we can have complex zeros, but they will not be x-intercepts. They will not cross the x-axis, and they will not be factors. If a factor occurs m times, it's said to have a multiplicity of n. So for example, in this function, f of x equals x plus 3, we say the real 0, negative 3, has a multiplicity of 2. That means it occurs twice. If a factor occurs n times, right, that's its multiplicity. If it has odd multiplicity, that means our graph crosses the x-axis at our real 0. And an even multiplicity means our graph touches the x-axis at our real 0, but does not cross it. So let's find my zeros and tell me if the multiplicity is even or odd. So my zeros are when x is negative 3, negative 1, and 2. I want to know if there's an even or odd multiplicity. If there's an even multiplicity, my 0 touches my graph. If there's an odd multiplicity, my graph crosses the x-axis. So 3 and 1 are both going to be odd. Sorry, negative 3 and negative 1 are both going to be odd. and x equals 2 is going to be even because my graph just barely touches the x-axis.